of 100 people that visit a health center or health facility, you'll find that 40% or 40 of those 100 people are diagnosed with malaria. Yeah. Now, government strategies have been put in place to ensure that there is malaria vector control, and they have mainly relied on providing and distributing mosquito nets, that is treated mosquito nets, and the indoor residue spraying. But you know, and also there is in some countries, they're actually doing malaria vaccination for the little ones, which will possibly also roll out soon in Uganda. But tonight, our topic of discussion is new innovations for malaria vector control. With me in studio is Dr. Jonathan Kayondo, who is a principal investigator, Target Malaria Uganda project at Uganda Virus Research Institute. Doctor, a very good evening to you and welcome to the show.
Thank you very much, and good evening, viewers.
Okay. Now, Doctor, I believe government has really done a lot that every now and then we are sure we have seen them really effect the strategies. The messages have gone out. Now, when you talk about Target Malaria Uganda project, now, which one is that and how different is it from the strategies that government is using right now?
Thank you very much. Maybe before I start with the Target Malaria, I'll first paint the picture of the
overall picture of malaria situation in the country.
Because that's the basis for why we exist as Target Malaria.
Okay.
Yes. So if we look at the WHO recent report, they have a 2023 report that tries to look at the global progress, on how malaria is being controlled and prevented across the world. And with that, you can see our report card for Africa and also our report card for Uganda. And when you read through that, you realize that, of course, the situation when it comes to malaria is not where I would like it to be. It's still a big global burden, even globally. We still have more than almost 250 million, cases being reported in a year, and those are leading to nearly 600,000 people dying. Those are big number of people. But what's troubling is that when you look at the contribution or the proportions that are attributed to the various regions, Africa is bearing the highest burden. More than 95% of those numbers that I've talked about, come from Africa. So as Africa, we are disproportionately being, affected by malaria. When you dig further deep into the Africa situation and then come to our country, you also find that we are among the top 5 heavily malaria burdened country in the world.
Top 5?
Yeah, top 5. And clearly that's not where we would want to be. So that means it's serious. If you look at the figures, we also know it has an economic burden, to the country. We have losses, almost $500 million US, a year lost, economic loss as a result of malaria and so forth. So that really means that we need to be doing something. We need to be doing more, to fight the disease. So that's one part. Now, obviously, the good part is that malaria is preventable. It still remains a preventable disease, even though it's struggling. And also the good part is that, like you've said, government has really shown commitment, and we also have the world also showing resolve to fight malaria. So that's there, and that's working for us. And of course, also we haven't reached a limit of what we can do, to tackle the disease. There are a number of things that probably should be doing that we are not doing as well. Some of the tools that we have, we're not using them optimally. Probably there's a way we could use data more to improve on how we strategize and target some of these interventions. And at the same time, of course, we also can come up with new innovations that can help complement, the existing innovations. And of course, there's always the issue of resources. It's expensive, and we don't have an unlimited resources, so that would always be a challenge. But the hope is that if we could bring on board new tools, new innovation, probably work smarter, probably we can eradicate. So the problem has always been, if we want to aim to be bolder and try to dream eradication, that's why we feel that more needs to be done, and that's where Target Malaria comes in. on the part of new innovations. Obviously, the bottom line is that we should not be acceptable that people, especially young children, continue dying from malaria, that expectant mothers get complications due to malaria. You know, that the poor are disproportionately affected, you know, by malaria, that Africa bears the highest burden of malaria. So we shouldn't accept those things, and we should be doing everything that we can to at least reverse that, because in a way it really affects our economic development, putting us in a vicious cycle of course, ill health, and then poverty, and then slowed economic development, and then you're in that, and you can't really get yourself out. So Target Malaria, we believe that there's something we can do, that we could bring additional innovations into the malaria control, and that's why, you know, we formed ourselves. So in terms of who exactly we are, I would say Target Malaria is a network of professionals who are constituted as a consortium, yeah, of researchers and other experts coming together or formed to develop a novel technology for malaria vector control. And this technology, we hope that it's going to be innovative, it will have innovative aspects to it, and that it could complement existing tools, and hopefully together, you know, we can eradicate the malaria. The consortium is comprised of different members, and they are scientists and other experts that are based in institutions that are found in Africa, in Europe, and in the US. Such an undertaking obviously requires lots of expertise, lots of people collaborating, working together to come up with, you know, all the additional skill sets and come up with, you know, product that could of course be more innovative and try to bridge some of the gaps that we see with existing, you know, methods of control. So our innovation basically is, you can think of it as a biocontrol tool that works, let's say, uniquely in different ways that are innovative, whereby we harness genetic modification in order to reduce the numbers of the mosquitoes that transmit the malaria.
Okay, now just how many countries are involved in this whole, you know, Target Malaria? Like you in the consortium, like from like which countries? Because Africa is like among the highest, like you said, but, and when you talk about us ranking number 5, it's kind of scary. So I appreciate the role of the scientists. How many are we all together, putting together heads together towards it? And is it cutting across, or you only have one country where you're first starting with the core experiment?
No, so it's so in Africa, in the Target Malaria Consortium, we have at the moment 3 countries, you know, that are actively involved in the research. Let's say 2 core and 1 supporting. So that's the African contribution. But of course, as the project goes through the phases, I'll talk about the phases later, so because it's a phase development strategy, we're open to bring up on board more and more countries. But at the moment, you know, there are 3 countries in Africa, and all of these, you know, high burdened malaria countries. Yes.
Now, in terms of, I would imagine, for us, the times every time you get to hear that there is a vaccine round the corner bound to be rolled out or so, we presume that that has now given us a relief and that's a solution. But you as the scientist are like, I'm coming up with a new innovation. What's your take on the vaccine? Do we think maybe like we'll get comfortable with it, but, and then now eventually the vectors will also just also keep on multiplying? Why the new innovation?
Yes. So malaria is very hard to control and fight. As you've heard before, the government has put in a lot. Countries are really trying the best they can, but it still persists. So expert opinion is that you're not going to be able to defeat malaria with only just one tool. If you're talking about eradication, yeah, then you have to bring on board more tools. So it's like having, you need a toolbox that have all these options that you can throw at the disease depending on what stage you're at and depending on the area, the location, and lots of things. So the vaccine is good, but the vaccine alone is not able to eradicate the disease. The vaccine that's most promising now is mostly helpful in the young. Of course, yes, the young are the most, vulnerable, of course, but it also has its limits, but it contributes. But if it's complemented with these other tools, including ours when it gets ready, we hope we'll have a package that hopefully together can enable us to eradicate the disease.
Mm-hmm. Now, what's this new innovation?
Yeah. So the new innovation that we envisage is of the malaria transmitting mosquitoes. So we have also to take a step back and understand what that means. So malaria is transmitted through the bite of an infected mosquito from one person to the other. That it's caused by a parasite itself, but the way it's spread from one person to the other, you need a mosquito to do the spreading or to bridge. Yeah, from a sick person to a healthy person, there's a mosquito that bites a sick person and then transmits those parasites to the healthy person. So that's how the cycle goes, and it's well understood, and we have a pretty good understanding of it. Now, we also know that it's not all mosquitoes actually that transmit the malaria. Actually, we know that there are more than 3,500 species of mosquitoes. Not a number of mosquito species, species of mosquitoes. And of those, we know how many species, for example, in Africa, about 800 species are found in Africa. And of those, we know which are the culprits when it comes to malaria transmission. So malaria transmission is sustained by a few species of mosquitoes. And when we come to Uganda, we also know which one to target. So this approach is quite targeted. It goes for the species that transmit the malaria and not, all these other mosquito species. And of course, it aims to target in specific ways, this mosquito that spreads the malaria, so that we can introduce a modification into it that targets factors or genes that are essential in its either development or survival. And that way, when those ones are disrupted, then you can have reduction in the numbers of malaria transmitting mosquitoes. But that genetic modification, to be able to do that in itself is not novel, because those ideas have been around for a long time. But it couldn't be turned into a practical tool until recently, because there's a small problem that one has to deal with. So that problem is, once you successful in the lab at creating a modified mosquito that has traits that, let's say, make malaria transmission not easily possible. For example, those traits could be, like in our case, reproduction, so that the numbers fall. And later on I can describe how that exactly happens. But let's say if you target that trait, we know it has a genetic basis, so you can go into the gene of the mosquito and target those genes and have a version that's now not able to reproduce or develop the way it should be developing. And if you achieve that, then you can affect the numbers of the mosquitoes that transmit the disease. But to do that with your modified mosquitoes from the lab, because it has to be a genetic approach, you need to find a way of quickly spreading that trait into your target population. If you just brought 1 or 2 or even 10 or 20 of your modified mosquitoes, the way the biology works is that there are so many outside there than yours, and so those one will just be a handful of them, and everything else being equal, there's really no reason why that trait should be transmitted to the other target mosquito population. The way biology usually works is, if a trait is not beneficial to an organism, there's a way natural selection comes in and doesn't select for it. So that means that that trait ends up dying down. It's not actually spread or promoted. That's how nature works. So to spread that trait, even though it's important to us and it's valuable to us, to the mosquito, that's not really valuable to it. and there's no reason why it should spread. So usually the fate of such alterations that are, let's say, harmful to the mosquito, because this one in a way it's harmful to it, is they reduce in frequency because those carrying it are disadvantaged in nature. And so it's the other one that don't carry it that actually are going to leave more children or offspring. And so you can't be, reducing numbers that way. But there is a natural mechanism that we can harness. And that's really where our innovation comes in. So this natural mechanism is a mechanism called gene drive.
Gene drive?
Yeah, gene drive, yes. It facilitates preferential transmission or inheritance of particular trait, whether they're useful to the mosquito or not. So during ordinary inheritance, usually, you have to imagine an organism, and the mosquito is in a type where we call those kind of organisms diploid. So that means they have 2 copies of each gene. So those 2 copies, one came from one of the parent and the other came from the other parent. So they're diploid organism. Each gene, you can imagine, just 2 copies. So usually during reproduction, such an organism usually has a fair, an equal chance of transmitting one of those copies to any of the offspring through the gametes during reproduction. So each copy is equally transmitted to the next generation. So there's a half-half chance that that's going to be the case. And so that's fair. And with that mode of reproduction, you really can't spread a trait quickly enough unless if it's beneficial and then nature helps you with it. But if it's not, it will not. Now what gene drive does, it biases that fair inheritance of traits, and instead it then now preferentially selects for one of them. So if you have a trait that's under a gene drive, then that one, it will always be selected, it will always be transmitted to the offsprings most of the times. And so therefore you can then see that with time, if each one that gets it spreads it to most of its offsprings in a few generations, then that trait can start spreading. And if that trait is the one that, let's say, confers ability to suppress the numbers or any other trait that you may want to introduce that help you with malaria transmission, then it becomes a practical tool. So with gene drive, we can now have a modification, introduce it into a natural target population and hope that it can spread because the gene drive will be helping it to be favored, during reproduction.
Wow, that seems like, how should I say, a process that's going to take long, because I'm imagining by the time you get to the numbers that you want, and also I'm imagining now for the first trial, because as the researchers, the principal investigators, the scientists, there is normally room for trial. What are the chances that this will be successful? Because from the way I'm hearing it and from the way I'm seeing the process it's going to take, and I don't know how long you have planned for phase 1 to take place and which is the targeted area. Possibly you would like to take me through that.
Yeah, but maybe let's start a step back.
A step back, okay?
Yes, yeah, on the why this is novel. So ordinarily, if we were not harnessing that gene drive, yeah, what you will need to do is what you're saying, be prepared to raise tons and tons of mosquitoes so that when you said come to releasing them, they'll be numerous enough at least to be able to either match or even exceed the ones that are out there in nature, because that's how they'll be able to mate with the wild ones and then transfer that trait and then hopefully it spreads. But if that wasn't the case, then the numbers are against you. Yeah. So then what makes our technology innovative is that luckily for ours, actually you don't need tons and tons because it has this secret, let's say, weapon to it. It has this gene drive, yeah, that's going to help it, yeah, spread it relatively quickly through the target population. Those therefore there, you can start with few of them. You can even start with just a bucket of those mosquitoes. And if you release them, if they get a chance to mate, then that natural mechanism can take over and then preferably ensure that that trait, yeah, is the one that's, inherited by the offspring, and then those who carry it also when they mate in the subsequent generation, they also spread it. So with time, it should be able to not take too long, and you also don't need to hopefully do tons and tons of them. But still, there's still things to solve, because it still has to have a sexual encounter for it to be able to pass it on. Then you also need to see how your mosquito populations, how they're connected, because they have to encounter, these ones that are carrying the drive, and they have to mate, yeah, for it to start. So that also needs to be worked out, right? But then in terms of, let's say, whether it can be promising on how do you know it's going to work.
Chances of survival of the gene drive when you put it out into the wilderness.
Yes, and all those things. So those things up front you can't know, but then you need the research to be able to find out. So for us, the way we've designed our research for this is it's a staged approach. So we go through stages and phases, yeah? So on day one, we don't just come up and say, oh, here's the gene drive mosquito, so let's go see. No. So we start from a phase where we have a modification, but we don't have a gene drive. Because I told you the gene drive, what will help is when you want to release it later and you want it to preferentially, let's say, spread to the target population. But in terms of effect, the effect that you want to introduce, if let's say the effect is to, let's say, deactivate genes that are essential for, let's say, reproduction or development, that one you can make it without a drive being part of it. And then you can first study that and see whether that works as you have intended to. Usually, you know what traits you want to introduce, yeah? And so you know which genes you should be introducing or deactivating. So then you can create that first in the lab and first see whether it behaves the way you expect it to behave. For example, if the aim was to modify so that we have one that, let's say, affects the ability to, say, develop, and say, let's say, it ends up, say, skewing the sex ratios to, let's say, more males, that can be a pathway to also reducing the populations, because we know that first, males don't bite, it's the females that really bite and spread the disease. Yeah. So if you modify that, during that's modified results in children or offspring who are mostly males, then you know that in that next those offsprings, the males happened at the expense of the females which were biting. But we also know that the number of the mosquito population in the subsequent generation is directly proportional to the number of females that are there. So as you keep having more males at the expense of females, you start reducing the number of females available to bite, but then also to reproduce the next generation. So with time, you can keep lowering the numbers of females, and at some point, you reach a level where you can curb the malaria transmission. So that can be one flavor of that. But you could also have another flavor where you just directly target genes in the females that affect development or even fertility. There are lots of options that you could take, but again, the same concept there. If you introduce those in the lab, and then still in the lab, you check whether it's behaving the way you expect it to behave. So if you thought you modified to make it less fertile or lay fewer eggs, then those type of females that are modified, you expect them compared to the non-modified to be less fertile. And so then, as long as that trait keeps spreading, then you know that eventually it's going to do its purpose. But first, you do them with one that doesn't have a drive, but just confirm the assumptions that you have and make sure it works the way it should work, and make sure it's only that you've targeted and not other things, and make sure you know where your modification you placed it, because you're placing it in the genome, and satisfy yourself with a number of things. Check for safety, check for whether that modified mosquito is toxic for any reason just because of the modifications. Those are experiments that you can run in the lab, and check its other behavior. Does it feed maybe more avidly than the non-modified one? And that one you can check in the lab even without going out, And if it does, then you have to go back to the drawing board, because because our promise is we can modify it in specific ways. So you only want to target the trait, and the other trait should remain like in the wild type. And you could,
But docile.
yeah.
I would imagine, because now
Yes.
when you talk about all that, in my head I'm busy thinking. You talked about the bit of the feeding. Yes, we know it's the female mosquitoes that will do the biting and all that.
Yes.
Now, as you go phasing them out, let's assume in terms of fertility,
Yes.
how does the how does this gene drive survive? You still keep getting and you know, producing more in the lab as the scientists, or how are you going to go about it if you lower the fertility of these ones? Yeah. Or if you do some kind of science, like you said, and then they're not able to reproduce. So when you phase them out, what happens eventually, assuming the females are all done? How does the gene drive survive? Or does it also die out eventually after some time?
Okay, that's a very smart question, and if you actually think deeper, that initially looks like a conundrum, because, for example, if you talked about something that causes, let's say, infertility, then how are you going to spread? Because if it causes infertility, then that should be fertile, then they should die with that one, and then they shouldn't be spreading. But luckily, either biologists are lucky, or sometimes we get a break. And so the way genes behave, sometimes you have genes that, because we have two copies, so sometimes some genes can be dominant. You just need just one copy to overtake the other one, and so that its trait is what, you know, will drive. But for this one to work, you really need to make sure the gene you've targeted is what we call haplosufficient. So that one means that it can be there, but if it's in just one copy of it, it will be recessive to the other one. So as long as you have it in that state, that it's not dominant, then in theory, when a mosquito has only one copy of your, let's say, infertility gene, the other normal copy should be able to do its work, and so that mosquito can still reproduce, and then this infertility part can still be transferred to a normal one, whose offspring will also get it as half of the copy, and the other copy will be normal. So first, it will spread by being what we call heterozygote. So there'll be two copies in each, but it will start kicking in when those heterozygotes become now the dominant one, and then when they start meeting, when you do the biology, the crossing, you'll then see that now the offspring from those crosses, half of them are going to be like, they are going to be homozygous. They are going to have both copies, let's say, of the infertile gene. And then when that happens, then for them now they're done. So that, you know, they'll terminate, they will not produce the next generation. So there's that phase where it can spread when it's still, you know, heterozygote. But it's during the design, you have to really look careful and make sure those are the kind of genes that you use, so that you are able to, you know, spread them. And so that takes some time. Yeah. So there's a way. So let's say biologists and molecular biologists have a way of, you know, designing it and, you know, overcoming that one. But in the end, it's still able to spread.
Then what about the fact, how are they still, how is the gene drive still going to survive in the nature of, remember, we do our own spraying mosquito, you know, they are the treated mosquito nets. Is it going to be able to survive that? Or it will also, you know, it easily, of course, would possibly get affected by whatever we spit out in the environment to prevent mosquitoes.
Of course, it will get affected. So in our design, our modification is quite specific, and we're targeting just a particular trait. So everything else will be like a wild type mosquito. They'll only be different only when it comes to the trait that we targeted. So, for example, just because it's a gene drive, it will still be susceptible to insecticide. Just because it's a gene drive will not make it able to avoid, say, drought. It will still be killed, because it's like the wild type or the natural mosquito. The only thing it has that's different, for example, if we introduce that trait of, let's say, infertility or some form of altered development, is only that. The rest will be the same, because we'll have checked in the lab to make sure we have compared it with the normal counterparts and made sure that, you know, that's the case. But still, we still test them in the lab, at least to make sure that at least they feed like the others. They're really not different except in just that one aspect. But still, you're right in the sense that when you get a laboratory reared mosquito and you try to use it as a tool for malaria control in the real world, that's a different environment. Usually in the lab and in the cage, we can get fantastic results and they can look very good and capable. But in the field, it's now different. In the field, because in the lab, we are looking after them. We feed them. You know, we control the temperature. They don't have to face rain. They don't have to face predators and all that kind of thing. In the wild, it's different. They have to now know how to survive. They'll need to know where to locate, where the plants are for nectar. They'll need to find for themselves the host to bite. They'll need to know how to deal with predators. They'll need to know how to shelter themselves, you know, from rain and all that kind of thing. But most of all, they need to be able to compete with their counterpart males that are not modified, who are more adapted, you know, to that environment. So early on, you don't know that. But you start in the lab and at least check that first it's safe, the safety things, you make sure you know that's not an issue. And then in the field, that's where usually you worry about things of efficacy. So if it comes to doing, let's say, releases or trials, one of the things that you'll be looking at to say, you'll be saying, okay, well, in the lab, we're very impressed with what we saw and it looked promising. Can it also, you know, replicate it also, you know, in the field? And then you learn a lot. And sometimes you may find that maybe it's a little bit not what you expected, and you may need to improve a few things, but in the end, that's also part of the pathway. So in terms of the development pathway, we have phases where it's lab work, it's under containment, and we're just checking its performance with its colonized counterparts that are not modified, and making sure that the only difference they have with them is just the trait that we introduced. Everything else is the same, and they're safe and everything. Then when that's complete, then you have to then go to that other stage where now you have to see whether they can perform now in your life. And so that's our field release stage, and it's part of the, you know, regulatory pathway. But first, this lab stage informs you a lot about the design that you'll use in the, you know, in the field stage to test that. And then you first do that in a controlled manner, again, in a way, because you still have to show that there's some impact. So usually it's still a study that you design, because the aim is, because it can't be just you saying that in the lab we saw. You have to demonstrate it. So you have to sort of demonstrate it. But that's a different process. It's still part of the research. It has lots of requirements, you know, regulatory approvals and everything. You have to compile doses, lots of things.
When you're talking about it now, I'm just curious to find out at what stage are we when it comes to the gene drive?
Okay.
Is it still on the paperwork stage? Are we at the lab stage? Are we at the trial stage where, you know, you have selected specific communities to do the trial? What stage are we at?
So when it comes to the gene drive, it's still in the lab stage and not even in our Ugandan lab stage. So for us, we say the path because I described a consortium, each one doing different bits, contributing different pieces. So for Uganda and even, you know, a lot of others, we also still, even the evaluation now is also phased. So we first evaluate a version that's not driving first, just as a proof of principle. Like I said, that when you claim that you can modify a mosquito in specific ways, so that's a big claim. So you have to demonstrate it and show it. So we say, okay, let's show it, because we are saying two things. We can modify a mosquito in specific ways, and we can harness gene drive to spread those traits. So those are two pieces, but we can decouple those. And so the first part that we start with is what they call proof of concept, to show that first, it's even possible to at least modify in specific ways. So right now, in our lab, we've just been finalizing what you call setting up the infrastructure and laying the groundwork, you know, for this kind of thing. So we are now poised to start working on a modified strain in the lab, but it will not be having gene drive. It will just be for the proof of principle and to see how that fares against an unmodified ones. And at the same time, it's also an opportunity to build capacity in terms of handling genetically modified mosquitoes, because that's going to be the first, even for us, because it hasn't been done. So we have to do it, but you didn't want to start with a gene drive. Okay. So you start with that one, you perfect the systems and all the protocol, and we have, usually that kind of work takes place in a specialized laboratory. We call it an insectary, but usually has like recommended containment level for biosafety reasons. It's a requirement. So we follow those, and so we have a facility that meets those kind of specifications, and we've dry run it, not using modified mosquitoes, but the wild type mosquitoes, and we can attain excellent measures of containment. But now, of course, we will need to make sure that it can support our modified mosquitoes, but initially those without drive, and then our protocols are fine, the data captures and lots of things, and also operation experience, with this type of mosquitoes. But first, we have the gene drive. So that's where the Uganda research is. Now, after, if that goes well, and we are happy with the findings, and we are happy with the modification, and we see that our assumptions held, and that it's competitive compared to the unmodified ones, which are under captivity in our lab, then that gives us a good basis to say that, well, I think now we can move now to the next stage where we can start, thinking about the gene drives, and then maybe trial, or maybe even setting up trials. But a lot of what goes into that will have to be collected, and most of that capacity will have to be acquired during this phase. But of course, there are also other questions that also need to be answered as we go along. Like I told you, for example, when it comes to talking about a gene drive trial, that trial has to be designed, but then you design it with the specific strain that you're going to be handling. And when that's out, we should be in position to start coming up with those. But at the same time, you also have to select sites, of course, based on a number of criteria. So right now what we've been doing is doing field studies in a number of sites and trying to understand the dynamics there, because the results there will inform us which is the ideal place to, to consider even designing, such kind of work when it comes to the field stage. But at this point in time, there's a lot of data collection that's going on. There's a lot of refinement of things, even a simple thing like, say, how do you transport a modified mosquito? Because if you're going to release, you have to transport it, right? Do you have the logistic? Even now, we don't know what's the best way.
Have you also thought about the sensitization bit of it? Because you can imagine people in a particular area where you're going to conduct the trial, and here you're going to introduce the gene drive at the stage when you have finally modified it. And then they might go and say, hey, these guys have come and they have spread more mosquitoes in the area.
Yes. Yeah, that's a very important question. So part of our pillars, our research is based on, say, 3 pillars. Sound science is one. That's the one we've been focusing on. Will it work, whatever, and those safety. That's very important to us, and we take it seriously. But equally important are 2 other pillars that one I've touched a little bit. Is called the regulatory compliance. The research, the gene drive, and let's say biotechnology in general is very heavily regulated, and for good reason. So there's a lot of regulatory requirements that you have to go through, and lots of regulatory oversights. So that's the other pillar, that we have to comply. And they usually give guidelines on how to do this kind of work in a safe manner, and in a way that you are not be harming human health or environmental health and other things that could be important. So that's the other pillar. We have teams that are dedicated to that kind of thing. We have experts or professionals that do that kind of work. They're experts in that, so they really contribute to the project and help us in that regard. Now the other pillar which you've talked about is the one for stakeholder engagement. So our strategy as Target Malaria is to co-develop this technology with others, and more importantly, with the people who will be the ultimate beneficiary. That's a new approach of doing things, but we think it's the best way to do it, especially when it comes to a technology of this kind. So right now, you've not been seeing us on TV or anything talking about, because like I've told you, our work is going in phases. So the first phase was just setting up infrastructure, laying the foundation. Yeah. So for that, there's really not much to say except just saying, here we have this a new facility, a new state-of-the-art facility that we've put up. And the other one was routine data collection. You catch mosquitoes in the field so that you understand the species composition, let's say, in an area. You understand the biting behavior. You understand how do they breed. Yeah, where are the breeding sites? You try to understand what else, maybe sharing breeding sites with them, and the dependencies and all that kind of thing, because that will be important when it comes to the downstream, phases, when you have to, because you have to know what you're dealing with before you start saying you're going to try and control it. So that part was not involving, or is not involving genetically modified anything. So for that, the engagement that we've done has mostly been limited to the, the study site communities and through the regulators and all. But you're right. Of course, when it comes to GeneDrive, we have to, enhance our engagement. We have to escalate it, even wider, and we have to work with the potential, beneficiary of this technology hand in hand. So the best way is to explain, what the strategy is, and of course, most scientists, you want to have your ducks aligned first before you start going spreading things. But at least, if looking forward with the stage where we are at, we have firm expectations that we will begin the lab work with a non-GeneDrive version, and then that will be leading us to a future GeneDrive. So we can start talking more about what it would be and its benefits, but most importantly also allow time to ask lots of questions. Of course, a lot of questions are also asked when you're going through the risk assessment yeah, but usually those are expert people who ask, but then also the study community also need a chance to also ask and anything that may have of concern, and that can be factored into the design. And luckily, the reason we did a phased approach is to build in time into the whole pathway for those kind of discussions.
You're talking about time. My final question to you is, what is your timeline? What timeline are you giving yourselves? Because, when you talk about it, for me, it sounds exciting, and I can't wait to see an innovation, especially where technology is involved, and we are able to get done, like you'd say, end malaria by this period of time. Yes. So what is the timeline that you're giving yourselves as Target Malaria Uganda project to see that we are rolling into action, the public is sensitized about it, there are efficacy issues, and we are able to kick malaria out of Uganda?
So one thing, in terms of our timelines, of course we have to go through the phases. So we have the phase where we are working with this version that's not GeneDrive, but we want to check its performance and all those kind of things under containment. So we think if all goes well, probably it could take us 2 years, to wrap up those kind of and really look at the data. Then we have another data that we need to collect regarding, let's say, the behavior of our mosquitoes and what site could be ideal depending on how the data pans out. That will be able to help us select candidate sites for the next stage, which could be field evaluation of some point. So for that and all the logistic things that we really have to overcome and design, we are thinking probably on our side it could take us 3 more additional years after the 2 years. So we're talking about, let's say, in 5 years we may be in a position to say we have a product that we are ready to evaluate as a tool for malaria control. So we are thinking probably 2028, 2029. But then again, there are also other things that are really out of our hands, because not everything really depends on us, the investigators. Like I said, we are very compliant with regulatory systems. So the regulatory systems expect a dossier and it expects lots of data that talks to the safety profile of those strains, and also the environmental component and any risk assessment reports that go to it, because you have to check, because it's not only just efficacy, it's also that part of it. Of course, we are confident that, of course, our technology will not have, harm to the environment or the human health, but it's not, you don't just say that.
And to the
you
other
have to
species.
bring the data, exactly, yeah. So,
The
so
other
that takes
insects.
time. Yeah, exactly. And then usually those are done by independent people. Usually it wouldn't be you again to be saying, okay, I did this. So you can do your bit, but ultimately it has to be an independent, risk assessment, and also an independent impact assessment to also at least corroborate your result. And but to start it, you need to work with a specific strain, and until that's there, then you really can't go for. But there are some other things that can start. So we're still in that, and there's still some work to be done. But if everything pans out as we expect, then hopefully, maybe, we could have something that we could be saying we are ready to see whether it could be a tool for malaria control. But maybe what I want to also point out is we don't think that the gene drive is going to be a magic bullet. We've been in this malaria control sphere for long enough, at least. We've gone through the highs when, for example, chloroquine was discovered, and we thought that's the magic cure, and we know how that happened. And then there was the DDT era came, and we were very excited. And then, so we know gene drive on its own will not. I can almost bet
Comfortably say
by
it,
itself, yeah, because when I understand the way the biology works, and you have to understand that, as I said, the gene drive itself, it's not a magic thing. It's a natural phenomenon. And in nature, organisms have found a way to counter it. So we don't think that, the mosquito will be any different. It may be just a question of time, but eventually it could. And also, gene drive can also suffer from resistance issues, not the one for insecticide, but a different, because the way it works,
The environment.
yeah, you have to target it in a specific sequence on the genome. So if that sequence somehow mutates or changes, then it's gene drive proof. Then it can. So all those changes are possible. Of course, as scientists, you can design it and say, okay, I'm going to target multiple places so that they all can't, or I'm going to target places that are hard to mutate. Those are also part of the design. But the way the natural biology system works is you have to be prepared to manage it and deal with it. But what we're saying is that it brings features, yeah, that help help cover some of the protection gaps. If you look at some of the methods that we are currently relying on, let's say for vector control, I'm going to restrict myself to vector control. So we mostly rely on insecticides, and one of our mainstay insecticide is pyrethroid or pyrethrum or pyrethroid insecticides, and those ones are used in the nets, yeah. But we know that mosquitoes are becoming resistant to it. So resistance is emerging, yeah. So they're not as efficacious, as they used to be. Yeah, as they used to be. On top of them just being able to tolerate it, they're also learning how to change their behavior to avoid them.
They are feeding even patterns.
Yeah, their feeding patterns are changing, and we can see that. So, and of course, the mosquito net can't protect you all the time. You can't say even during the day, I'm going to be in a mosquito net. Then you still have to leave. You still have to be productive, and you can't just, for people who have, let's say, latrines and everything, even at night, you can't go to your latrine with a net on it. So there are those gaps, that's our tools, yeah. So if you think about spraying residual insecticide, that's our main method. Again, the same thing. The mosquito will just catch you outside. They don't really have to come and, if it's not resistant, they'll wait for you outside, bite you a different time. If you're thinking of, let's say, habitat removal, cleaning up, that one can happen. But again, you know the type of mosquito that we are facing for the malaria elimination, the breeding site that it uses, they're this very small and very numerous, so it breeds in the pits left by bricklaying activities. It breeds even in the hoof prints of cows and livestock.
understand.
And those can be many everywhere, and some of them even inaccessible. So that's a challenge. Too numerous accessibility issues. So if you think of, you could say, okay, I'm going to do area-wide fumigation, maybe get helicopters and just spray on a wide scale.
It's not sustainable.
But that too, first of all, not sustainable. Then two, you have to worry about environmental degradation because of the toxicity that you introduce. So whichever one you think, there are those things. But now what this one comes in, it has advantages in that it can help us counter some of those, because in the gene drive model, the mosquito is doing the control for you. It's the one that's spreading it, on your behalf. So for you, for those people who say the net is too hot for me, I don't want it, the gene drive will take care of it. It will spread even when you rest comfortably. I'm not saying you don't use the net, but sometimes people don't get treatment because of accessibility issues, like they can't access, the either health facilities. But in this one, it doesn't rely on such infrastructure. Sometimes it's the systems that are weak in certain places. This one should continue even when that's the case. So there are features that it adds into the fight that, if combined with others,
we will fight and we'll be able to kick malaria out of Uganda.
Right.
Well, Doctor, we've run out of time. It's just about 3 minutes to the top of the hour, but I would like to say thank you so much. And for me, it's exciting to see that you, the scientists, are not seated just back and comfortable with the strategies of the malaria vector control in place, but are still coming up with new innovations. Thank you so much for your time, and we do appreciate the information and the education you've shared with us. It's just about a few minutes to the top of the hour, and at 10 o'clock, Rod and Gonzi will be coming your way with the news. It's good night from me, and definitely from Dr. Kayondo. Thank you so much.
Thank you very much.
Okay.
Yes. Yeah.
UBC, inspiring Uganda.